Now we're going to learn one of the most important continuous random variables, which is the normal random variable. So I'm actually going to jump straight into the definition first, and then we'll talk about why it's so commonly used. But basically, I define a normal random variable with two parameters, a mu and a sigma. Specifically, the mu will be the mean, and the sigma is the standard deviation. So the sigma squared is the variance. It is this famous bell-shaped curve, also called a Gaussian, after Friedrich Gauss, who was a major cheerleader for this distribution. And here is the PDF. And so, yes, it looks like a lot happening all at once. We're going to break it down in a minute. But I will point out that underneath what looks like somewhat of a scary PDF, there's a lot of really nice mathematical symmetry and useful intuition that you can get from this equation. So I will point out that the expected value is mu and the variance will be sigma squared. Now we're going to come back to this, but why is this called the quote normal distribution? What makes it so normal? All right, so things you may hear is, oh, well, it's because natural occurring phenomenon are distributed normally, like heights or weights. Or people may say, no, well, most noise in the world is distributed with a normal distribution. Or you may hear, well, it often results from the sum of many random variables. Or sample means are distributed normally. Let me debunk and confirm. Let me tell you which of these are actually true, because you'll hear them often. In reality, the natural phenomenon is actually better modeled with what's called a log normal distribution, which we won't be covering in this class, but just to clarify, it's not actually a normal distribution in a lot of cases. And then the most noise in the world being normal, that's actually just an assumption. There's nothing inherent in the way that noise from some type of like measurement device or some other type of thing that you're collecting, it's no reason that it would have to be normal, but oftentimes we assume that and then move forward to do our analysis. This idea of the sum of many random variables being normal, it is true, but only if those random variables are independent and equally weighted. So that's a special case. And last but not least, in good news, it is true that sample means are distributed normally, and we're going to prove this in our lesson on the central limit theorem. So, okay, why normal? This still didn't quite answer it. I'm going to give you another reason, because it's kind of nuanced here as to why this has become the distribution of choice. So suppose you have this data of heights of students from one classroom, and you decide, I want to model it. I want to come up with some distribution that models this data. Sure, I can fit the data with this dotted line that I have on this picture here, but in a lot of cases, that's going to suffer from what we call overfitting. Because as soon as I gather data from another classroom, it's not likely to fit this exact dotted line. And so instead, we can use a normal distribution with the same mean, the same variance as I would have had up above, because it generalizes well. It's basically a way to make a simple assumption for what the distribution may look like hopefully without overfitting. And it really does come from this idea. In general, the simplest solution is probably going to be the best, or at least a good starting point. There is another more complex mathematical justification as to why we would use the normal distribution, and it's actually because a normal distribution, or a Gaussian, maximizes what we call the entropy for a given mean and variance. Now, that is out of the scope of this class as to maximizing entropy and why that's useful, but at the end of the day, it's basically a way of saying it's a simple assumption we can make about the data with little information. So a lot of times we will, if we have, data that could roughly be fit by a bell curve like this example, we're going to go with it as a simple generalization for a starting point. And last but not least, the actual normal distribution mathematically has some amazing properties that make it really easy to use. So that's basically the third reason that we're going to see this so frequently. Okay, so let's go back to this so-called normal distribution and break apart some of the pieces in this PDF. The key things that I want you to focus on when you're looking at this is really this x minus mu term is basically going to make your distribution symmetric about mu, your mean. And then dividing by the variance is going to manage the spread. So the larger the variance, the wider your distribution is going to be. And then this piece out front is really just a constant so that the area underneath the normal curve is 1, so that our PDF integrates to 1 and it's a valid PDF. And this e to the negative power that we have here with the square is what's leading us to have these exponential tails. Okay, so let's practice just matching these different Gaussians to their corresponding means and variances. So go ahead, put it on pause and see what you come up with. Okay, a good starting point on this one is I noticed only one of these Gaussians or these normal distributions is shifted over and centered at -2 instead of 0. And so right away I know that this yellow dotted distribution is going to have a mean of -2. So that matches there. Now the other three are all centered at 0, and so now I need to compare their variances. And so if you remember, a wider distribution comes from a larger variance, and so this purple one has the widest distribution. Again, the reason the peak is lower here than here is because the area underneath all of these curves, each one individually has to be 1. So that's why this peak has to be smaller so that you keep an area of 1. All right, so the purple one has the largest variance, so that's going to match to number 3, a variance of 5. And then the blue dotted one has the narrowest or the smallest variance, and so that's going to match to number 4. And so what's left is a normal distribution with a mean of 0 and a variance of 1 is what's called the standard normal distribution. So sometimes you'll hear that phrase. That's a standard normal. All right, so another interesting property about the normal distribution that distinguishes it from other distributions we've worked with is usually it's not easy to visually estimate a standard deviation by just looking at a PDF. You usually have to do the calculation. But that's actually not the case when looking at a normal distribution, because you can show mathematically that the point of inflection, and so I've tried to highlight that here, that's where your PDF goes from what we call concave down, or think of it as like a frown, to concave up, think of it as like a smile. The point where that switches is called the point of inflection. And if we come down here onto the x-axis and look at that value, the standard deviation is the distance between your average, so the middle point here, and the points of inflection on either side. So that distance right there will be your standard deviation, which I'm denoting with sigma. And you can prove this using calculus and by finding the inflection points of that PDF, and you'll end up showing the inflection points occur at mu plus or minus sigma. So let's put this into practice. Go ahead and put this on pause. And for each of the distributions below, see if you can approximate the mean and the standard deviation just looking at it. All right, in good news, all of them have a mean that appears to be 70. So let's put that down for all of them. All right, now let's look at the standard deviation for the first one. So I'm going to sketch the rough PDF on top of it, and then I'm going to identify roughly where we go from concave down to concave up. It looks like right around there, right around there. I'm tracing down, and that's going to get me right to around 80. And so that means my standard deviation is this distance between those two, 80 minus 70, which looks like about 10. Same idea here, but you can see now at this point, it looks like my inflection points are happening now basically at 71, which is 1 unit away from the mean. So that's going to give me a standard deviation of 1. And then lastly here, it appears roughly right around 72. So the distance between 70 and 72 would be my standard deviation, and that's giving me 2. I just happen to look to the right. You're looking either way because it's symmetric, right? So you could have looked at 68, you could have looked at 69. On this one, it's going to give you the same approximation. Another cool fact about the normal distribution that distinguishes it from all other distributions. So if you recall, this was Chebyshev's inequality that let us make some conclusions about the percentage of data that was within certain standard deviations for all distributions. Well, the normal distribution, we can get even more specific because we can actually calculate this area underneath the curve. And it turns out the area underneath the curve, if I go plus or minus 1 standard deviation from my mean, gives me about 68% of the total area under the curve. And if I go plus or minus 2 standard deviations, I get 95% of the total area. And plus or minus 3 gets me to basically 100%, 99.73. So let's try this. Suppose I tell you the scores on a college entrance exam are approximately normal with mean 52, standard deviation 11. Just with that information, you can tell me that 68% of the scores lie between what two values? Put it on pause and see what you get. Okay, so we know 68% of the scores, or 68% of the distribution for a normal distribution lies within the average plus or minus 1 standard deviation. So I'm going to do 52 plus or minus 1 times 11, which gives me the interval 41 to 63. And I know that 68% of the scores are in that interval. Okay, now what about values other than those 3 percentages? What if I wanted to calculate the probability that a normal distribution was less than some specific value or in between specific values? This is where having the CDF would be really useful, just like we saw with previous distributions. However, the CDF involves integrating, like we know, this PDF again. So visually, if I want to find the area underneath the curve up to x, I'm basically asking for what's that integral to here. That's what that's meaning. All right, spoiler alert, there is actually not a way to do this in what we call a closed form, meaning I can't write this quantity any simpler. I can't get any closer to it right now. There's not like an integration technique where all of a sudden I can use integration by parts or U sub or something to get a nice formula in a closed form way. The best I can do is analytically or numerically approximate the value of this integral. And we do have very good numerical techniques where we'll imagine splitting up the area underneath this curve into tiny little rectangles or tiny little trapezoids and make them smaller and smaller and get a really good approximation. Or we can use Taylor series and get a good approximation as well. So we have techniques at our disposal for approximating areas under curves when there's not a perfect closed form solution. But we're going to put that in the hands of Python because doing those techniques and those approximations are beyond the scope of this class. So takeaway, we can't solve this analytically. So the best we can do is use built-in calculations already in Python. In good news, we can use SciPy. And again, it has a stats.norm.cdf, which is exactly what we'll use. So it is doing that numerical approximation for this value behind the scenes for us. All right, so let's try this in a problem. Suppose you spend some minutes traveling between classes. You know your average time spent's 4 minutes, and say the variance is 2 minutes squared. At this point, we have to make some assumptions. So let's say a simple assumption is to say, let's assume x is normally distributed. In that case, what's the probability you spend greater than or equal to 6 minutes traveling? Go ahead, put it on pause, see what you get. Okay, so again, we're setting up this integral, but here we're stuck until we get to Python, right? So let's switch over to our notebook, and we're gonna do this exact thing in our notebook, and we'll also plot it so we can visualize exactly what this looks like. Now we're gonna jump over to the continuous random variable notebook and scroll down to the normal distribution with Python section. So notice there's built-in stats.norm.pdf.cdf, and I had put in the slides the mean and standard deviation were your inputs, which is correct, but the words that Python uses for the mean is actually loc, and the word that it uses for the standard deviation is scale. And just to make it even more slightly confusing, when we write a normal distribution like this, we would put the mean, but we put the variance, not the standard deviation. So you have to be careful when you translate this into scipy.stats.norm that you can enter 4 for loc, but for scale you have to do square root of your variance. So that's going to lead us here. If I want to calculate the probability x is greater than or equal to 6, I'm going to do 1 minus stats.norm.cdf. I'm going to put 6 in here, and loc is going to be the mean, and scale is going to be the standard deviation. And that's going to give me basically a 0.786% chance for this problem. Let's go visualize that, and then we'll come back and compute the probability it's between 3 and 6. So if I want to plot what this means in part I again am going to need to use the PDF because that's going to give me the bell-shaped curve. And so here I'm going to do stats.norm.pdf, putting in x here, and then I'm going to just make sure I have that my center, my mean is 4, and my standard deviation is the square root of 2. And then I'm going to plot this, and this area here is what we were just calculating, and it's approximately 0.078. Now, let's say I wanted instead the probability that x was between 3 and 6. So I want the shaded area underneath this curve between 3 and 6. Well, now I can take the area underneath the curve up until 6. So let's copy this part here. And then I can subtract off. So stats.norm.cdf 6, loc is 4, scale is np.square root. Then I'm going to subtract off the area underneath the curve to the left of 3. So stats.norm.cdf 3, and then again with this mean and this standard deviation. And that would get me that area instead. So in terms of calculating probabilities for normal distributions, since there isn't a closed form solution, you need to use Python, or I will have to provide you with Python output so that you could answer with the output I have provided. So let me show you an example of that. Let's pop back to the slides and we'll do our last example. Suppose x is normally distributed with a mean of 114 and a variance of 144. What's the probability x is equal to 120? And then what's the probability x is between 111 and 116? And I put some potentially useful output from Python. So here's an example of how this might show up on a quiz or an exam if you didn't have access to Python while you were doing the quiz or exam. So again, put it on pause and see what you come up with. Okay, first one. So if you recall, for a continuous random variable, the probability that that random variable exactly equals any single real value is 0, because we define probabilities as areas underneath the curve. And so I need an interval of values to define that probability. But I can do this for this interval from 111 to 116. And in particular, I notice, I would be trying to do this integral, which is, like we said, not possible in a closed form way. But we realize that's the same as taking the area to the left of 116 and subtracting off the area to the left of 111, which is exactly what these are doing for us in the stats.norm.cdf. So I'm using those, which is that value right there, and then this value right here. And together I can subtract those and I get 0.17. So we will see the normal distribution show up throughout the rest of the course, but this was just an intro into its beauty and some of its nuances. Have a normal day.